Alrighty, I think this is my turn. Excited about this for a number of reasons. Reason number one, I think this is the first time that I've introduced Justin to a talk when he wasn't talking about steam engines. So that's achievement unlocked. Also, equally excited because Dan's in DevRel at Equinix Metal, so he's one of us. All right. So I don't think I need to necessarily get in the way. I know what this talk is all about, but you don't. So let me give you a quick overview. Justin from Docker and Dan from Equinix Metal are going to be talking to us about how we use LinuxKit to make Tinkerbell better, but I'm not going to spoil any of the surprises. Are you both ready to go?
Yes,
we are, I think.
Excellent. All right, take it away.
All right, I guess I will share my screen and kind of kick things off, and we'll kind of pass the baton back and forth. 1 second.
I see you're wearing your Windows 95 t-shirt.
I am. I'm bringing it back old school. Yeah, absolutely. And we're going to try and cram in quite a few demos here as well. I did want to try and deploy Windows 95, but unfortunately, I just couldn't find any hardware old enough where I could get it to actually deploy successfully. So unfortunately, that won't happen today. But yeah, we'll kick things off. Thank you very much for coming to this talk. This is all around Tinkerbell and LinuxKit and the magic that LinuxKit kind of brings to Tinkerbell. Quick introduction, Justin, would you like to quickly introduce yourself?
Yeah, so I'm Justin Cormack. I'm the CTO at Docker. I'm on the CNCF TOC, so I spend a lot of time with projects. I'm also someone who likes hardware, and I've been involved in LinuxKit for a long time, and I'm Tinkerbell is really exciting to me because I think that bringing hardware to bare metal is really important. Sorry, cloud native to bare metal.
Excellent. My name's Dan Finneran. I am leading the engineering team inside DevRel at Equinix Metal. I was also part of Docker. I was kind of randomly invited to work on a secret project called Moby at the time. And I don't know if Justin knows this, but I didn't actually know any Go when I was actually invited to work on this, but I was too nervous to say no. So I kind of quickly learned as much Go as possible in order to kind of contribute and be part of this project called Moby, which ultimately was then rebranded LinuxKit and was kind of my first foray into kind of working with Docker. So that was
we actually hire lots of people who don't know Go, and we've always had this view that there's no reason why you should know it up front. So yeah, if you're interested in cool stuff and you don't know Go but you're happy to learn it, we're hiring.
Excellent. Cool. So this is our agenda today. We're going to kind of quickly go over what Tinkerbell actually is and kind of how it hangs together, how LinuxKit, what LinuxKit actually is, and how we've added that magic into Tinkerbell. We're going to then demo how we're using LinuxKit to build some part of our secret source. And then hopefully my plan is to deploy 3 operating systems kind of back to back across 2 different types of hardware using a number of different types of technologies as well. So I've got a lot that we've kind of crammed in today. So kicking things off, what is Tinkerbell? So Tinkerbell is a project that originally came out of Packet, now Equinix Metal. And Tinkerbell is, to a certain degree, Equinix Metal / Packet's secret source. The technologies that power kind of Tinkerbell have basically come out of the technologies that powered Equinix Metal. And through that, the technologies that allow Equinix Metal to provision and give you as a resource bare metal infrastructure at speed. So Tinkerbell is effectively a bare metal provisioning engine. I have to put this slide in every bare metal presentation that I actually have. It has no actual reason to be here other than there is a bear kind of singing metal. But Tinkerbell, what actually is it? So Tinkerbell is a cloud native provisioning engine. So when we say that it's cloud native, and I'm going to cover this in a little bit more detail later on, it kind of makes use of a lot of kind of cloud native technologies. It makes use of a lot of cloud native themes and a lot of cloud native behaviors. And effectively, it's kind of a workflow engine in that you can give it a workflow, and it will execute that workflow as a series of actions on a remote host. What is an action? An action actually is a Docker container. So it allows us to kind of immediately make use of kind of obviously the kind of container paradigms. We can put in a particular task, bundle that up as a container image, and as that workflow is executed on a remote host, the code that lives within that image is then executed on that remote host. So for instance, we may have some code that would install the Grub bootloader, or some code that would wipe a TPM. The workflows are free flow. It's entirely down to you in terms of what it is that you would want to do with them. But this is kind of the start of the journey of like all of the technologies that we have decided are fantastic and we can kind of make use of in kind of enhancing kind of the bare metal deployment journey. As I mentioned, it's kind of a cloud native design. We make use of a number of microservices. So Tinkerbell is built from a number of different services that all hang together, and it allows us to swap and replace some of those services for different use cases. And then finally, this tooling allows us to kind of modify these various components. It also allows us to build and create operating system images, or through some of the use of LinuxKit, change the kernel that we may be using to deploy on a specific piece of hardware. So a kernel for a different architecture, or add and removing drivers into that kernel, dependent on the piece of infrastructure that we're deploying on top of. So how does Tinkerbell actually work? So we have a piece of infrastructure here with the MAC address, which is its burnt-in address of bad coffee 00. When we power this machine on for the first time, it has no knowledge of what it actually should be doing. It will effectively ask the network what it should actually be doing. Now, if you see this on a laptop, that normally means that your hard drive has died, or your hard drive has been wiped, or something has gone wrong, which isn't necessarily a good thing. But if we are provisioning infrastructure, then this is kind of what we actually want. And Tinkerbell will answer the call in this and start to get your blank server up to a point where you can actually make use of it. So quickly, how does it all hang together? Well, as I mentioned, it's a number of microservices, Tink server being kind of the brains of the operation. Using the CLI, we will effectively put in a hardware configuration matched with a Tinkerbell workflow, which again is more YAML. We live in a cloud native world where YAML needs to be everywhere. Once that is actually in place, once we've added this information into the Tink server, when the machine then actually boots, a microservice is now aware of it called boots. That microservice uses a number of technologies that are pretty old. DHCP will give it a network address. TFTP will send the kernel and the RAM disk in order for that machine to boot for the first time. And HTTP will typically be where various other assets are introduced. We can't change these technologies, unfortunately. DHCP, TFTP, and PXE are the de facto technologies that are still required to this day in order to provision infrastructure. And the spec for DHCP came out when President Clinton took office, and the spec for PXE came into to life when he left office, and nothing has happened since then. So all of the technologies that we use as of today are from the Clinton era, and there hasn't really been a huge change since then. So that's kind of how old these technologies actually are. Once this machine has been given the kernel and the RAM disk, it will boot that, and that OS that it will actually run is called OC, which is the in-memory operating system for provisioning. And inside that operating system is the Tink worker. Now, this is the engine that actually executes actions. So the Tink worker starts, it reaches back to that Tink server, where that Tink worker will be given the workflow, and it will start to execute those actions on this host as kind of a provisioning task. So kind of like the way in the Matrix where we could plug in Neo and tell him and give him new skills, we can actually then give a operating system the knowledge of something like Ubuntu, so we can provision through those mechanisms. So why LinuxKit? So as we kind of took the Tinkerbell project and started to kind of use it and work with the community, we kind of realized that some of the components were kind of having issues in how we were working with the community. The first part, an OC, is one of the main parts that kind of powers what was Packet, now Equinix Metal. It was incredibly tied to that infrastructure. To actually get OC to begin with, it was a multi-gig download, which a number of people were having issues in areas where they didn't necessarily have the greatest of broadband. If you wanted to actually work on OC, just getting the actual repo to begin with was a 16 gig download. So it was kind of quite hard and unwieldy to actually work with. As I mentioned, it was just very intertwined with the existing infrastructure. And it was kind of quite hard to build and work with as well. So it was kind of an hour from start to finish of building your brand new in-memory operating system. So with all of these things in mind, LinuxKit, and with that, I'm going to hand over to Jason.
Justin. Yeah, so yeah, I'm going to give you a little bit of a historical tour because that's kind of the way I like to frame this. If you go to the next slide. Also, you're not going to use steam engines, but you're going to get some old Unix machines. So, Unix started off looking like this in 1969, and kind of this is, so this is Kernighan and Ritchie in 1969. If you go to the next slide, this is actually kind of Unix as it kind of became. This is the Sun team in 1982 with the first Sun workstation, shiny and colorful, and very much recognizable as being the modern desktop Linux workstation in pretty much every way. It has, sure, you've got more packages now, but the kind of way you use it and the kind of running applications, if you log into a Sun workstation, if you dig one out on eBay, you probably find it very familiar. And it's really where a lot of what we got comes from. And what I'm interested in is actually really how we got away from this workstation view of Linux towards Linux as an appliance, which is where LinuxKit comes in. So if you go to the next slide. Oh, yes, this was, sorry, just 3M was the story. A megabyte of memory, a megapixel display, and a megaflop of compute for $10,000 was the kind of model, which is, we've now sort of a gigabyte of display and a bit more than a gigabyte of compute. But, it's sort of recognizable kind of prices have gone down and storage has gone up. Pixels haven't gone up that much, but next slide. The first big change in going from a workstation for people to automation was config management, which started with CF Engine in 1993 and really took off in the kind of 2000s with Puppet and Chef. And that was the kind of thing about, I was suddenly like, you can automate recipes. Originally, CF Engine was just for managing cron jobs across multiple computers, but it really turned into this kind of, oh, okay, I can tell a computer what to have on it, which again, you recognize from Tinkerbell. How do I get a computer to have stuff on it? But obviously that was from the point of view of already have an OS installed. Next slide. Virtualization was a really big change because before virtualization, you'd have a computer and you'd run everything on it. You'd run your mail server, your web server, everything on the same computer. Virtualization was the first thing that really encouraged us to have a web server VM and a mail server VM, and we'll manage them separately. And so computers started to have this role of just doing one thing. And again, with LinuxKit was really designed for this sort of idea of an appliance that does one thing. And you have lots of computers if you want to do lots of things, not one computer. Again, the whole workstation model was you have one workstation and you have everything on it. And again, really trying to move to the commodity model over time. Next slide. This was a really important talk given by CERN about pets versus cattle in 2012. This is really the beginning of kind of the cloud native thinking. So they noticed that they had these servers that they cared for lovingly and kept them going for many years. And then they had cattle, which were ones that were given numbers, not names, and they were almost identical. And then you would kind of automate them. And again, they would be using config management to do that. And they recognized that they wanted to move away from these hand managed pets into this kind of disposable, reusable kind of let's automate and deploy kind of model. Again, this was really a kind of important milestone in that cloud native journey, in how we use Linux. Next slide. CoreOS, this is Giphy Day, so it's really important to talk. CoreOS was not a Google project, but it was obviously a very much a Giphy project. And it was really, I remember when it came out, it was the first thing that got me really excited about that there's something new in cloud native. I've always been interested in Linux distros, and it was really the first radically, let's rebuild the Linux distro on a cloud native base. I thought it was absolutely incredibly exciting, this idea of this thing called etcd that would manage your etc. Across a cluster of machines was really kind of radical, and those kinds of things really got me interested in this space. Again, I think it was incredibly influential and influenced the kind of thinking in LinuxKit. But one of the things was it was really complicated to use. It was built on Gentoo, and it had many Git repos, and it was like, how do I get started? And one of the things with LinuxKit really was about massively simplifying this experience. So next slide. So 2015, we started LinuxKit. I was working on Docker Desktop, which was then just Docker for Mac, and we had a terrible kind of Linux distro, that had been built for Docker Toolbox that was really unmaintainable. And if you click on it, it was we wanted something simple and embedded. And I think if you look at the first commit, my message says, not required, self-update, treat as immutable. So right from the beginning, it was like, this is not about something that updates itself. It's about something that's really totally disposable. You build it and you deploy it. And I think the next bullet is really, I think the next point was, it's really the idea of actually a cloud native endpoint. We're really driving with LinuxKit towards there being, we started off with a YAML config file because that's kind of easy. But it's really moving towards just having an API that you can create Linuxes from. And we're getting quite close. I think there's still more work to make it really more of an API endpoint. People have actually put it at the end of an HTTP endpoint that will generate images for you, and it's kind of cool. But that's the model we're aiming for, is really you want a Linux running these containers here, call this endpoint, we'll have you one built in a few seconds, and you can deploy it. And that's really the model. And it's an appliance, it's reliable and disposable, it's immutable. With Docker Desktop, you can press the reset button, it resets it all to the known good state, and so you know that it'll just boot up the same way. And for we have millions of users, and we have to make this really reliable. We can't have a state that we're not in control of with LinuxKit. So that's really the genesis of this whole thing around really just how can we make this a small, simple, embedded, immutable, and cloud native as possible. And in the demos, you'll really see how that kind of works for Tinkerbell.
Excellent. So thank you very much for that overview. As you know, the technologies in LinuxKit really allowed us to kind of move past all of those issues that we kind of mentioned and we faced. The architecture of LinuxKit really kind of lent itself well with what it is that we were trying to do. So, kind of with that introducing hook, like everything in the cloud native space, you kind of have to stick with a theme for your naming. Unfortunately, in the Peter Pan space, there is not necessarily the greatest selection of names to go for. We probably will have something named Wendy in the future. I'm not entirely sure what that will be yet, but Hook is the name for effectively our community in-memory operating system that we use LinuxKit to actually build. So LinuxKit, in the way that it works, it will build an operating system from a set of container images. So we We take the LTS, the latest Linux kernel. We have taken basically the basic configuration from the upstream kernel.org, and using LinuxKit built a kernel that effectively everybody can use. But it is easy for you to build your own kernel, as mentioned, with those different drivers or different architectures. We make use of a number of other images that come as part of the LinuxKit project. So it will bundle together all of the bits to effectively start the other containers that are bundled into the LinuxKit hook OS. We apply a terminal at the moment. So Getty is effectively will give you a CLI that we can use for debugging. At some point or another, we may remove that. It can be easily replaced with an SSH container, so you can debug over the network as opposed to requiring direct access to the machine. A DHCP client is a requirement. This all uses networking, so if a bare metal machine comes up without a DHCP client on there, it will just sit there at that point. It won't be able to speak to the Tink server and get all of those components that it needs. And then these are the two parts that we actually added to make it, in our minds, hook. The bootkit perspective, which is an image that a container that runs first, that will set up everything that is needed for hook to run. So it will get certificates from the Tink server, which allows it to speak to repos, and it will set up the environment. And then the final part, which is the final piece of the puzzle, is hook Docker. And this is effectively Docker in Docker, which the Tink worker requires in order to execute those actions. So building hook, I'm just going to kind of quickly pop to a terminal. So what I have here split into, I'm going to kick these off quite quickly. I am using LinuxKit right now to build two operating systems at once. The one on the left is for x86, and the image on the right is going to build me a brand new operating system for ARM64. So I can use this in-memory operating system on the left for Intel infrastructure, for Intel hardware, and on the right-hand side, it will provide me a kernel and a RAM disk, all of the bits that I need in order to provision on hardware such as ARM servers, things like Raspberry Pis, etc. We can see as it's stepping through, it's getting all of those containers that are built multi-ARP, and it will effectively then put us together an operating system from all of those. And as I mentioned before, this used to take the best part of an hour to go to build as an operating system. It is doing the last step of this right now. So,
one of the things with LinuxKit is that it feels really annoyingly slow now, because operating systems used to take an hour and now it takes a minute, and it's like, why doesn't it take 3 seconds? We're still because that's that funny thing that once you've got rid of 99% of the time, and then you no longer have an excuse to go out and get a cup of coffee, and you're like, well, this is still too slow. So we're still working on making this faster.
Yeah, I mean, you can't use, was it that XKCD thing where it's like, I get to work, it's like, I can't, I'm compiling at the moment. It's like, it's too quick now. We've got no excuse anymore. So this effectively shows us how quick we can build that new hook in memory OS. And that allows us to effectively add and remove things. So as I mentioned, if we wanted to add SSH in there to add remote access for debugging, we've had kind of members of the community and people look at adding in metrics and monitoring and other things. Some of the things we're looking at, auto discovery, DCIM, and these we could just add in, rebuild, and then immediately make use of very quickly. So we can iterate very quickly with the community. So let me just pop back. So yeah. So that's building hook. Now we're going to quickly step through deploying on bare metal. Unfortunately, as I mentioned, I'm not going to be able to deploy Windows 95, but I will kick off by deploying. Let me just make sure I do this right, because if I get this wrong, my demo will completely implode. So we're going to kick things off. I'm going to quickly deploy Windows 2016. So I will start off by trying to find the right window. There we go. And I'm going to reset this machine to boot from Pixie. So at the moment, I have two physical machines. There's a Kubernetes cluster at the moment, and I'm going to completely repurpose it for a different use case. So I'm going to reset this machine from Pixie. So the machine on the right is now going to reset, and it will reboot, and Tinkerbell will effectively take care of provisioning Windows 2016 on there through those workflows. whilst that does happen, then this window will tend to bounce around quite a lot whilst it's taking place. So I'll need to keep my eye on that. So whilst that's actually taking place, what I'm also going to do is I am going to use an OCI compliant registry. So this is one of the new things that we've added recently. And we can see here I have Harbor installed as a registry, but this will work with any OCI compliant registry. And I'm going to push an ESXi image to that registry. So we can see here now that there's an ESXi image that has been pushed to that registry. And what I will do now is I will create a new workflow which will use a different type of action that will stream an OS image directly from a registry. And I will kick the other machine off.
And this is using ORAS, which is the OCI artifacts tool, which is a really cool tool if you want to play around with sticking other things in registries.
Yeah, absolutely. So the images, the way that the actions that Tinkerbell can make use of, there are a number of them that are all available on Artifact Hub. So if we kind of search for Tinkerbell on here, we can see here there are a number of actions that we've open sourced, and image to disk will stream directly from a web server, any web server. OCI to disk, it imports the ORAS packages, and it effectively will allow us to do basically a Docker pull and take that compressed stream and then write that directly to a block device. So where's the other window? So we can see here what's actually loading it. It's not the prettiest of thing, but on the left, well, on both sides of the screen at the moment, the Hook operating system has been loaded over the network. We can see the LinuxKit whale. I don't know why I'm pointing, can't see my hands. The LinuxKit whale appeared for a split second, and that operating system is being streamed directly to a block device inside that system. The machine on the right has finished provisioning already, so that's 90 seconds or so to deploy Windows 2016 using Hook to do all of that and write that directly to there. So Windows 2016 should start booting on the machine on the right. The machine on the left is going to reboot into ESXi. So that logo should look familiar to some. And this machine is going to start booting ESXi. One last thing that I'm going to do is quickly show some additional functionality. And we're going to reboot the Windows machine, and we're going to provision Debian on there. So this basically shows us how quick we can kind of move between different operating systems. And this allows us to kind of work in a bit more of a cloud native way. We can pave over things quite quickly. So deploy Windows or deploy Debian or do whatever it is you want to do with things. If something breaks, we can effectively reset it back to its original configuration using these images. So one last step. So these are the workflows that I created. I'm just going to delete the workflow and I'm deploying a new workflow that will use a Debian, and I need to make sure I push that actually to a registry before I try and use it. So if we see here, we should see there's that Debian, and we can see that the ESXi was just pulled. And if I quickly go back and reset that other machine, one second. This is the last step. And one final thing about this as well. This demonstration is going to use a technology called kexec. So instead of us having to power, so here's the finished deployed Windows machine. That's going to power cycle in a second. Instead of us having to do reboots, which on larger machines would incur the cost of power on self-tests and iterating through all of the hardware and things like that, we can deploy very quickly in that we can write that operating system to the block device. We can use an action which will auto-discover the grub config that's been provisioned on there, find the new kernel, find the new RAM disk, and use a technology called kexec to basically jump straight into that operating system. This allows us to move very quickly, and in some of the other integrations that we're looking at, so things like Cluster API Tinkerbell, we're going to be able to use that technology to basically deploy in a comparatively same level playing field as you would do in a cloud-like environment. So stream that OS directly to a block device and then just pivot directly into it. Debian's quite small, so this should be very quickly. So 25 seconds, it's now deploying Debian to the block device. And this should take maybe another 5 or 10 seconds or so. This is a live demo, so I deserve something to break at some point or another. Oh, no. Okay, that took 21 seconds, and it's now kernel execing directly into that. So no reboot. We won't see the Intel NUC logo or anything like that. We should see in a second the Debian prompt as it's jumped straight into that OS. And there we go. So no reboots or anything like that. We have pivoted directly into that new OS, which allows us to move very quickly.
Very good.
Thank you. So I think that kind of wraps up the 3 operating systems that I was aiming to deploy in 3 minutes or so. The last kind of couple of things that I wanted to touch on quite quickly, things that we're touching on. So as I mentioned, OS images in OCI compliant registries. So that allows us to get all of the benefits of OCI registries. Signing of images. So we're looking at how we can kind of go about doing that. Having pipelines to build those images that we can deploy. We're making use of Packer to do those sorts of things. Enhancing hook, so we can add in bits and remove bits that we need or don't need. And one final thing is an action that actually contains the application itself. So, installing an OS was okay. Streaming an OS is cool, but how about just actually running the application? So we don't actually need to write anything to the bare metal. We can basically have that application and just get our bare metal to run it. So is this serverless? I like to think of this as OS-less, and that's my my new technology for KubeCon 2021 is OS-less. And with that, yeah, do we have any questions?
Alrighty, that was a whistle-stop tour. We don't actually have time for questions, although I'm sure there will be a lot, but don't worry, it was all action-packed stuff. And if anybody does have any questions, you can come and contact us either through Twitter, BSD Box, I believe. Well, just Google it. Oh, there we go. It's on the screen. Justin, I can't remember yours, but if you Google Justin Cormack, nice and easy. But yeah, we're over time. We've got to get into the next one. So Justin, Dan, thank you so much. That was incredible. And you can also go to the Equinix Metal Slack, which is slack.equinixmetal.com, and go to the Tinkerbell channel, where you will find all sorts of Tinkerbell related goodness. Thank you all and goodbye. Okay.